time you're just twiddling thumbs, we might as well get that going, and then we can come back to theory. So if you haven't done this stuff already, go ahead and create a GCP account. I'm not going to go over that step because it's unique for everybody, but effectively it's just entering in that credit code that you got from me or that you'll get from Liz. You'll want to make sure to add the credit code via this link right here. It means you get free $5 of compute power. You are free to use that for Bitcoin mining after this course, but please first use it for this course. And then let's move on to this slide. So I'll talk about this more when we get to the theory portion, but when you're using Spark or you're using effectively a Hadoop cluster, Hadoop needs space to store its information. And you can store the information in a lot of different places. Because we're in the cloud, we're going to store our information in a cloud bucket. So let's go ahead and create one of those cloud buckets. I'm going to go to councilgoogle.com. I'm going to move all y'all faces over just a bit here so that I can select this. Close that window so I don't get confused. There we go. I've already created this project. Okay. If you haven't, go ahead and click new project there, create your project, and then come back. And let's do one thing. First, let's go over to Dataproc. So I'm clicking on these 3 bars up in the upper left-hand corner. I scroll down to Dataproc. You can sometimes search for this, but every once in a while they change the UI. Just go ahead and scroll on down until you see Dataproc, and it will be under, here it is, under Big Data. Okay, I already have it pinned. When you click on Dataproc for the first time, it's disabled, and you have to click Enable. So I want you to go ahead and click Enable. You will not see Cloud Dataproc, create cluster. You will see Enable API. Do that. Then, once you're done with that, let's go ahead and create the bucket that I spoke of. And we need cloud storage for that. So I want you to scroll down to storage.
Oh, hi, Professor. I have a quick question. Yeah. So in the guide for how to set up the account, it says to link the billing account with our projects. And then when I click enable for the cloud data prop, it says billing must be enabled for the activation of service to proceed. But my project under billing said the billing is disabled. So like how do we enable the billing in order to proceed in this data prop?
Well, let's go down to the billing section under more products, billing, what have you. And go over here, and it takes a hot second. But you should see something like this kind of a page. You should see 5 credits that are assigned to you, or $5 worth. I have more because I teach a bunch of these classes, but you should see something like that. And then if you click on manage, you'll start to manage the billing account itself. Okay. And then there's projects that you can link to this. You should see your project listed under here.
Okay. I think I found it. Thank you.
Okay, great. Yeah. And if you need to, you'll click change billing, and you can change the billing to a different account. You just need to make sure that the $5 account, the account that contains $5 is the account that's associated with your project that you've spun up.
Okay, great. Thanks.
Cool. Good question. All right, so we're going back to cloud storage. Once we're in cloud storage, which is going to be under here under the major section of storage, you'll need to create a bucket. Okay, and I'm going to go ahead and delete these buckets so that I can start all over again. And delete. This actually might not allow me to do this since there's data in some of these. Oh, okay, great, it did. I'm going to copy that. Let's create a bucket. I'll name this -2. You name the bucket whatever you want. I suggest you name it the same thing as your project because it's just easier to remember. It's easier to copy and paste. What is a bucket? It is effectively an infinite drive, a drive that scales to pretty much whatever size you want. It might not be the fastest drive that's out there because it is a networked drive. It's a drive that you have to connect to over the internet rather than something that's connected to your machine right here, but it's there and it's very scalable, right? It's often referred to as a data lake in a lot of places, especially in data analysis. Data lake because it's just so huge. There's just so much space for all the data you can throw into it. And it's globally unique. So if you create a bucket in GCP, you will own that bucket. No one else will have that bucket in GCP. It's not prefixed by your name unless you add the prefix yourself. It's just your bucket. You kind of claim that name. Most of the time, people won't find your buckets. People aren't trying, at least in my experience, to like find buckets out on the web. So you'll still have to share links, but ultimately it's there and available. So I'm going to click continue. I'm going to choose where to store my data. I'm going to say multi-region. I could have it in a single region. I think that probably makes more sense if you're doing data analysis only in one region. It'll give you slightly faster progress along your machine learning operations. But if you need to make sure that your data persists no matter what happens, say, a comet hits the planet and takes out a data center, you want your data to survive somewhere else on the planet. And so that's what multi-region solutions are for. It's the default, and I'm going to leave it as such. I'm also going to say that I want to leave it at standard. I can have nearline, cold line, or archive behavior for my data. Leave it as standard for anything to do with data analysis because you want to access that information again and again and again quickly. If it's a nearline, cold line, or archive, you're going to incur lots of costs that you wouldn't otherwise because you're accessing the data so frequently. The assumption when you're using one of these other services like nearline or cold line is that you just don't access that often, so you might as well store it away. They give you a cheaper price so long as you don't continuously try to access it. I'm going to flush over permissions because permissions are super complicated. And finally, how to protect your data, that is more permissioning and lifecycle policy stuff for your data. Basically, when does it get dumped out of when does it get deleted out of the solution? Leave those as the defaults as well. Okay, and I'll click create here. And it creates my bucket, and it takes only like half a second. And now I have this bucket where I can store information up in the cloud, which is super awesome, right? So I've created my drive. Now let's go back, and we're going to create a Dataproc cluster. Our Dataproc cluster API should be enabled at this point, right? So I should now have the option to create a cluster. I want you to click create cluster. You'll give it a name. You can use the default name, really doesn't matter. I do want you to choose a location that's closest to you. So I'm in or on the West Coast. So anything in US West would be fine for me. I'm gonna do US West 2 because I'm feeling like US West 2 today. And I'm gonna stick with a standard cluster type. So I'm gonna have one master node and multiple workers. And I'll specify the number of workers later on. We also want to change up the versioning to not use 2.0 Debian. I want to use 1.5 Debian. You can use the more updated versions if you update the code, but I have not updated my code yet. So I just want to use the older versioning. I'm going to click on Component Gateway. This is going to allow me to access via the web these different components that I'm going to enable. And I'm going to enable Anaconda, and I'm going to enable Jupyter Notebook. Okay, so within this cluster that I'm creating, and I know I haven't really explained what a cluster is yet, just bear with me. Within this cluster that I'm creating, there's going to be certain things installed, and I've given it a hard drive, right? Because I've given it that cloud storage bucket, or at least I've created the drive for it. And I've also specified the applications that I want installed on the cluster, Anaconda and Jupyter Notebook being them. Then let's go to configure nodes. A Spark cluster, a Dataproc cluster, is made up of some amount of master nodes and some amount of mirror nodes or worker nodes. We do not need this much disk, and to save you all some money, let's drop it down from 500 to 50 gigabytes of persistent disk for our master node. You can leave the master node type as an N1 standard 4. That's plenty of power to get what we're doing today done. And then we'll leave it at 2 worker nodes. It'll help our explanations later on today if we have 2 worker nodes. But we can also drop its disk down to 50 gigabytes. We certainly don't need that much disk. And that should be it for the configuring nodes section. Let me double check my notes here though. And yeah, that's all we need in that tab. Let's go down to customize cluster. You can leave almost all of this as is, but under scheduled deletion, let's delete on a fixed time schedule. So we're going to delete this cluster at a specific time in the future, and that's in 2 hours. Oops, sorry. Delete after elapsed time since creation, after 2 hours. The reason is these data proc clusters cost a lot of money, and I don't want you to accidentally forget about this cluster being in existence and then use up all of your $5. That would suck, right? So let's make sure it deletes itself, and you can always recreate it later on. That's the beauty of the cloud. And then finally, we need to attach that hard drive that we created, that bucket, to the cluster that we're creating, right? We need to tell the cluster, this is where to store your data. So the storage staging bucket should be configured to be your bucket. I'm gonna click on that and select. I get a nice little green check mark over the bucket, and we're almost set. This stuff can all be ignored within security. Don't quote me on that. You should usually not ignore security, but again, this is just playing around here. So, and that's it. And then we'll click create, and we're off to the races. Now we wait around for 5 minutes while the cloud does its jazz. So let me see what questions came through. Oh, it wasn't a question. Elizabeth said something. I believe you've gotten to all across the team. Okay, great, cool. All right, so, whoa. What was that? I've never seen an error before. Hold on, everybody. Without local SSDs, we strongly recommend 1 terabyte and larger. Did you get that? Yeah. I'm wondering, did anybody else get this? Because I ran this just 8 hours ago before I went, or like 12 hours ago before I went to bed to make sure everything was up, and I did not get this issue. So I'm wondering if I chose a wrong zone. Stock Alberus bug? No, it's still provisioning. Okay. Oh, I'm just gonna create another one real quick. And I'll do it in a different, this is a region. So this is a great example of why you should create clusters in the cloud. If anything goes wrong, guess what? You just get to do it again, and it'll be just fine. Takes no time to retry. If you were to do this with real hardware, take forever and could set you back weeks in a Kana Jupyter notebook. And 500 because I want to avoid this error, and because I have the money to burn in my account, I'm going to leave it as 500 gigabytes. And I'm going to go over to customize cluster, choose staging bucket. There we go. Select and delete after fixed. Okay. And that was all I needed to do, right? Check my notes again. Yeah, okay. Let's give it a hot second. I just want to make sure this gets past the point of what we saw before. Give it maybe 5 seconds. 1,000. All right, that's enough to make me feel confident to go back to my slides. So let's talk about some theory. Let's talk about what we're doing in this lecture. What is data proc? Data proc is a package service that GCP offers, and it just wraps Spark. If you've never heard of Spark, well then, Spark is just an in-memory version of Hadoop. If you've never heard of Hadoop, well, what is Hadoop? Hadoop was this tool created back in the 90s for fanning out an operation over a bunch of worker nodes so that you could do this massive scale data analysis efficiently in a reasonable amount of time, right? So it was in the 90s when we started to get this really big ballooning amount of information, right? Back in the 90s, it was probably laughable compared to how much data we have today. I think like all of the information ever created by humanity, like most of it was created within the past 10 years or something like that. It's something insane, right? It's something, just a huge amount of data was created over the past few decades. And it became clear that, one computer is not going to be able to scan through all of the information that's out there and find what you need to find, right? You think about these big companies like Yahoo or Google, when they're needing to find something for you in a query, they're not having one single MacBook Pro scan through all the data for this, right? They need a whole fleet of computers to do this for them. And it's really impractical to build one big supercomputer to do it. Like, oh, okay, well, we'll create an index and search service for you, but we're going to create one big machine. No, that's a terrible idea, because I should back up. Somebody thought of that idea. It's a reasonable idea to start with. It's not a scalable idea, right? The reason is computers fail. Computers fail all the time. Just within the amount of time that we've talked on this call, that we've been on this call, several computers have failed in the data center that you're connected to, right? That's just how often these machines fail. So we can't create one big server to do this process for us. It wouldn't be serviceable to the general public, right? So what do? Well, we create some tool, some set of computers where any number of them can fail, right? And we have this fleet of computers work on the search service, right? So how does that work? Well, we need jobs to be able to be retried. So if one portion of the job fails, okay, fine, just retry it somewhere else, right? And we also need some way to fan out the effort and pull in the answers, right? And so this is where this term MapReduce came from, or at least where it got proliferated quite greatly in the past 20 years. The idea is you have some operation that you want to do, and you map that over all of your data. So let's say it's adding a bunch of numbers. You've got this huge slew of integers, just petabytes of integers that are up in the cloud, and you want to add all of them. Well, add will be your map operation. You're going to tell your fleet of computers that, hey, I'm giving you this chunk of integers to work on, and hey, computer over here, I'm going to give you this other chunk of integers to work on. And I'm going to map. I want you to map this add operation over your integers, right? Please do that, right? So that's the fan out portion. Then eventually you need to get all of those answers back. And so that's where the reduce portion comes in. After each node has summed its integers together, it's going to have that reduced form of the answer, and it's going to hand it back to its parent node, or maybe even to the master node. And then the master node will reduce that answer further. It'll basically sum up the previous sums that have already been calculated. And it'll keep on going like that all the way up the tree until you get a final answer, right? So why Spark then? Seems like Hadoop. If Hadoop is doing that, if Hadoop is doing that fanning out and MapReduce operation, and it can retry jobs, like, we're done, right? Why do we need more than that? Well, Hadoop works with information on disk. It was only really built, it's been scaled up to do other things, but it was originally built to look at information on disk and immediately read and write to disk to perform its operations. That is very slow. That is very inhibiting to the power of a machine that you're sitting on. When you're sitting on a machine, you usually have tons of RAM to play with nowadays. And so why not keep as much of that information in RAM as you can, and do as much of the computation in RAM as possible? And so that's where Spark came about. Spark was just built on top of Hadoop. And Spark attempts to keep as much of the information it's working on in memory while it's working on it. Let me see, something came up in chat. Somebody said got mine to work. That's great. Okay. Anyone else unable to create the cluster because of Jupyter image versions? Make sure that you're using the right Debian version. So it should be 1.5. So it's not the 2 by default. If I click create cluster and I go to here, versioning, you see how the default is 2.0-Debian 10? That shouldn't be the case. You want to change, yeah. You want to change that down to 1.5. Cool. So back to here. What else is great about Spark? It has been built out for ease of computation and ease of operation. Double operator there, but it's been built for the developer. Right? Hadoop was very complex to set up, very complex to use. It got amazing results for its time, but it was just hard to work with. So out came about Spark. And so, well, what is this Spark installation that we have? It's either a set of machines that we own running, or it's a set of machines that we rent, i.e. via Google's Dataproc service. And we run our services there. We run the Spark process over those. How do we integrate or communicate with Spark? We do so with some sort of Spark bindings. And there's bindings in Python, there's bindings in Java, there's bindings in C++. Basically, there's ways to talk to a Spark installation, which effectively kind of looks like a database in a lot of ways. There's ways to communicate with Spark in lots of different languages. But one of the ones I like the most is PySpark, and it definitely has an industry lead in a lot of ways because you're dealing with Python, and Python has kind of become this new language of data. What does PySpark and its bindings look like? It looks a lot like pandas. If you've ever worked with pandas before, you know it's kind of like the Excel of Python. PySpark tries to do the exact same thing. The difference is that instead of creating everything in memory or holding everything in the master node memory that a pandas data frame does, the Spark data frames, they contain instructions on how to compute their information, and they're only going to compute information at the very last minute. Once they do, then they'll hold the information in memory, right? Because that's Spark's whole appeal. Let's use memory when possible. I want to point out just how easy it is to use Spark. This is almost verbatim real Python. This Spark is probably replaced by Spark context, but spark.read.json looks very much like your pandas operation. You get back a data frame. And then you can do these operations like df.where or select, and you're getting SQL-like syntax. You can also do data frame operations like you would in Python. So a very powerful tool. Let's go to data structures that are available within PySpark. Before we do that, let's take a look at this question. Does Firefox run the GCP platform better than Chrome? I run everything in Chrome, but shows differently. No, it should run just the same. I'm running in Firefox right now. So, okay. So what are the ways in which PySpark holds its data? PySpark likes to holds its data in one fundamental data structure, and everything else is built on top of that. And that fundamental data structure is the RDD, or resiliently distributed data set. This is what allows a computation to fail and be picked back up by another node. Right? So let's say node 1 is working on a problem, it's summing up a bunch of numbers, and then somebody pulls the plug, or a shark bites on a cable, and suddenly now we don't have power to that node for whatever reason. You can come up with a million scenarios why a node might go down, but the node goes down because the RDD is the same data distributed over multiple nodes. Another node in the Spark cluster can notice that the node 1 went down, pick up the work where it left off, and continue on, right? So that's the resilient part. The distributed part should also be pretty obvious. it needs to be distributed such that another node can pick up the work if one fails, right? Then immutable, this just means that once you create a data set, it doesn't change. You make copies of that data set, and you don't necessarily copy all of the data in the data set, but you copy the state of the data as like a timestamp or as like an operation stamp. This is the data after these series of operations. And then when you ask for PySpark to do another operation on that data, you're going to end up with a new RDD at a different operation timestamp, right? And only once you ask PySpark to evaluate the whole series of operations will PySpark, evaluate all of the different states in between. For the same reason, it's lazy, or that's what I just said, is it only evaluates once you ask it to evaluate. This is for cost and efficiency reasons. You just don't want to be computing all those intermediary states if PySpark can find out that two states cancel each other out and it just doesn't need to do that work, right? There's also typing that's built into an RDD. So an RDD has this notion of this column is a string, this column is an int, and this gives a certain amount of speed to PySpark. If it didn't have this typing, you lose a lot of speed, and just because you're looking up the types and what operations are valid between two types. For example, that addition is a valid operation between two numbers. But what does it mean if you add a number to a date time? Well, you don't know, and you have to look up the operation for those two different types if it wasn't statically typed. Okay, and then data frames are built on top of an RDD, but they loosen up the type safety. They are very much like your data frames within pandas. They're not identical, but for the most part, you can kind of think of them as the same thing. And the types are not strict along the column. So that can be a little bit confusing. It can kind of slow things down. For the most part, it's not a huge concern. And as you get deeper into data analysis, you can optimize where you find it necessary. The way that you can optimize is with things like the use of data sets or tungsten, which make sure that your data frames are typed appropriately for each column. This might mean that you have to go back through your code and make sure that the code is updated to ensure that only the right types end up in a specific column. But once it's done, then you know that, okay, great, I'm going to be able to take advantage of the type safety and the speed efficiencies that come with that, the speed ups that come with that. And then finally, if you're working with graphical representation or graphically represented information, so let's say you're working with a social network, then you probably are working not in relational data, but in these vertices and edges types of structured information. And there's a way to deal with that type of info within PySpark, but you're going to use a graph frame rather than a data frame, right? When I say graph, I don't mean a plot. I don't mean a Cartesian plot. I mean just dots and lines in between them, that type of a mathematical graph. Let's see what we came through. Is it likely for each node to successfully fail, leading to a cycle? Can you flesh that question out a little bit more? I'm not sure what you mean by successively.
Well, you said that a node can pick up the work from other nodes.
Yes.
If they fail.
Yep.
So is the cycle like one would fail, a new node would come along, it would fail, and you just kind of get stuck?
Yeah, that's certainly a possibility. It's pretty rare that you're going to have, well, it's just like any probability, right? The more times you fail, the less likely that series of events is to occur, right? However, if there's some relation, like you have a whole region start to fail because it lost power or something like that, then yes, they would successfully fail, but then your whole operation would fail unless it's distributed over multiple regions. I think if your question is, do you need to be concerned about that in your day-to-day operations? No, and especially not since if you're working on something like GCP Data Proc, because they handle that problem for you. Does that answer the question that you asked?
Yeah, it does. Thank you.
And then we have a question, is there a link to the slides? Thank you for somebody who posted that. Thank you, thank you. The guide has, yeah, great, okay. So, so how do we get started, or how do people get started? The early 2010s, people were doing it this way. You would hire several engineers, probably a team of 1 to 3 people that would work on setting up a Hadoop and then Spark cluster for several weeks, maybe even a month before it got operational. And that's a large amount of money. You're looking at least $100,000 to get set up for a production cluster. I mean, because GCP noticed this, and GCP wasn't the only one. It's just it's the only cloud vendor that I get free coupons for that has a grant with Columbia, right? There's other entities out there that do the same thing. But these cloud vendors, they picked up on this. They're really good at noticing when there is some hard technical infrastructure problem that can be automated away and then can be left with just like button clicks to get the same solution. And so they automated it away, and now they sell it as a wrapped service, which is very nice. And you see that we can set up a cluster with just a few button clicks, right? And I'd like to take a real quick tangent. The cloud vendors are really good at this, at picking up on services that are hard to set up and then selling them. Case in point, they already have a quantum computer for sale. Like, you can buy quantum computing hours right now. And that is like, it kind of just boggles the mind that came out a few years ago. Fun fact there. So let's do some data analysis on this PySpark cluster that we've set up. And to do that, we need to drop some data into our bucket that we've created. And we'll also upload a few playbooks or Jupyter notebooks that I have in that link. If you go to this Logsdon Education data proc, I want you to save the PySpark intro, and I want it not to be this one. This is a Python 3 version. I want you to save the Python 2 version. Okay? You can do that by clicking on it, then clicking raw, and you'll get this big JSON blob if you just click save. Okay, and save, and it'll save to your local file system. Okay, so now we have the intro. I also want you to save what's under Titanic, but I want you to save the test, the train CSV, and then the Titanic Python 2 data proc docs. So just in the same way, you click on them, you click raw, and then you save to your local file system. I'm going to give you maybe 10 seconds or 15 seconds to do that.
Okay, Professor. So if we save the raw, then it will be a TXT file, right?
If you save the CSV, well, I'm on a Mac, so I guess it might do something funky if you're on a Windows machine. Are you on a Windows machine? Sorry to call you out.
I'm on Mac. I mean, the Python 2, like the data proc, like when I open up the other one, like on the previous brand. Yeah. So the PySpark intro, when I click like raw, and then I use like Command S to save it, then it saved it as a TXT file.
Okay, so if that's what's happening, it shouldn't, but if that's what's happening, all you have to do is go to that file and remove the TXT. So check this out. Let's assume that this one had .txt at the end, right? And I'm getting a warning. Oh, you can't see my screen. Hold on. All right, can you all see my screen, all of it now?
Yeah.
Okay, great. All right, so you see that I'm changing the name of this Titanic file to titanic.txt. It's warning me like, oh no, are you sure you want to change it to .txt? You'll say yes. All it is just an extension that you're not changing the data at all. What you want to do is, if you have a file that's like this, just change it. Oops, don't double click, hold click to remove that TXT and just use IPNB, right? That's all there is to it, and you'll be set. The data will not change inside, and everything should work out just fine. Joshua says, on Windows, save change it at the very bottom from TXT to all files, and then remove the TXT extension. Thank you, Joshua. Cool. All right, so we should have those files downloaded now. Let's go back to the GCP console, and let's go down to cloud storage. Under cloud storage, I have at least one bucket, maybe two, and I want to go into this PDL dataproc bucket, right? It's the bucket that I created. And I'm going to create a directory, create a folder. I'm going to call it Titanic. I'll click create. And then I'm going to click into Titanic, and I'm going to upload the files test and train CSV. And
oh, sorry, I didn't follow. So, is this when we click into the cluster?
Sorry, no, this is under cloud storage. So if you go to cloud storage here, it'll be also under the storage section. So in between file store and data transfer, click on cloud storage, you go to browser, and then you'll have your bucket that you created at the top of class. Okay, it's only in here that you'll create a Titanic folder. And inside the Titanic folder, upload the test and train CSVs.
Oh, sorry, we also need to enable it. So I'm just waiting. So in the file storage, right?
In the file storage, yeah.
Okay.
You needed to enable cloud storage?
Yeah, so I still need to enable the file storage. So it takes, I think it'll take a second.
Okay, and out of curiosity, what region are you in? If you don't mind me asking, if you do, don't worry about it.
Yeah, I'm just in the business school at Columbia, so it's
Okay.
East Coast.
Okay. All right.
I saw the instances instead of bucket details. So when I go into the file storage, there are like instance and backups instead of like browser monitoring and setting.
You don't want to be under file store. Sounds like you maybe went into file store. Make sure you click on cloud storage.
Oh, okay. Makes sense.
Cloud storage browser. That's what we're looking for here. Cool. And then again, just drop in the data into your bucket and under Titanic. Even if you forget to put it under Titanic, it's okay. It's not the end of the world. You can work around that. Just as long as the train and test CSV files are up in this bucket somewhere. Okay, so we spent the first 45 minutes setting up. You know, it gets quicker and quicker every time. We could probably gotten in 10 minutes once you've gone through it a couple times. But now we're ready to actually start doing some of that data analysis, that sweet data analysis we're all looking to do here. So I want us to go back to dataproc. Okay. So under our left-hand section, under big data, we go to dataproc, and we're going to click on our cluster, right? Once I'm into my cluster, I'll see that there's these pages that says, you know, okay, here's how much yarn memory you have, and a bunch of other statistics about how the cluster is performing. We can ignore all of that. We're just going to go right on over to web interfaces. Okay. Under web interfaces, we have all the available web interfaces. We're going to click on Jupyter. And we have a really sweet Jupyter notebook here. Right now, we're starting to look like home. I don't know about y'all, but when you start to see something like this, you start to feel a little bit of reassurance, and the sweat is off, you know, from dealing with all that infrastructure back on home turf. The local disk folder corresponds to the actual local disk of the master node. We don't want to mess with that. We don't want to touch that at all. You can look at it, but don't change anything there, because otherwise you're changing the operating system information on that, on your master node. And then GCS is the bucket that points to where we store our information in our cloud bucket. So it's a pseudo pointer to a folder in our bucket. And it's here where we're going to upload our IPython notebooks that we downloaded. So I'm going to upload both. I'm going to upload PySpark, upload, and then I'm also going to upload this Titanic file. Awesome. Okay. I'm going to stop here just because it's easy to, maybe get lost along the way. So I want to make sure everybody's kind of on the same page here. Have we all been able to get to this state? Okay, I got one yes. All right, how did you jump to the Jupyter notebook from the bucket? Yeah, good question. So when I was in the console, this whole interface, this whole website is the GCP console. And when I was in the bucket area under cloud storage, I saw these kinds of things, right? So names of buckets. And under a particular bucket, I would have like Titanic and maybe the CSV files. And I'll go up to this upper left-hand corner and click on these three white lines, and I'll scroll down to Dataproc. Sometimes you have to scroll quite a while. It'll always be under big data though. Okay? And under Dataproc, you can either just click on Dataproc or you can click on clusters. Either one will bring you to this page. Okay. If you click on a particular cluster, then you can get to the Jupyter notebook for that cluster by navigating to web interfaces and then clicking on Jupyter. And that will pop open this page right here. Okay. So, great. I'm going to open up this first notebook, this PySpark intro, and I want to make special note of something. So I'm hoping most people are paying attention because it can kind of throw people off if it's your first time playing with PySpark. This looks like a normal Jupyter notebook. It says it has a kernel of Python 3 over here on the upper right-hand side. If I execute this cell though, it's going to say SC is not defined. And that's because we've started up this Jupyter notebook with a normal Python 3 kernel. We need it to be started up with a PySpark kernel. So we're going to change the kernel to PySpark. Okay. Then it says no kernel. That's fine because we just need to restart everything. I'm going to click Shift Return to get it going. And it's going to take probably like 15 seconds to run through this cell. This is where our Jupyter notebook code is starting to talk to the master node and saying, hey, it looks like somebody in a Jupyter notebook is starting to want to do some Spark stuff. Can you start spinning up a Spark context and spinning up all the stuff that you need to do good Spark computation? And the master node will say, oh, okay, great. And it takes a while to set all that stuff up. Once it's done, then you'll get back a result. Okay. And since we're within a PySpark kernel, we get this SC variable for free, right? It's just there, it's in the global namespace. And is there any significant difference between PySpark kernel or just doing the manual imports and setup? No, in my experience, no. Somebody that deals with this day in, day out might be able to tell you why one is better than the other. But in my experience, just dealing with the vanilla PySpark is plenty fine. So the Spark context has a bunch of different operations on it. The first one that I want to talk about is parallelize. And it's a way of telling PySpark that, hey, I've got this set of data. I want you to go create an RDD for me and then hand me back the RDD. right? So distribute the data however you think is best, and just hand me back a handle to that information. So PySpark underneath the hood will take this list 4, 10, 9, and 7, and it'll distribute it and duplicate the information over nodes appropriately so that if any one of our 2 worker nodes went down, we would still have the data replicated somewhere else, right? And then, so far, besides pushing that information out, PySpark hasn't done anything, right? It's just created the RDD for us. And then if we wanted to take 3 or like get 3 items from this RDD, we could issue the take method with the number of items that we want, 3 in this case. And that's where PySpark, the master node, would say, okay, worker nodes 1 through n, I want you to work on getting me back the first few items of this RDD. And then, you know, M through Z, I know I started off with 1 to M, but A through M, go work on the first few items of the RDD, and then M through Z, go ahead and get me the rest of the items, right? So distribute out that work. That's what the master node is there for. It's for breaking apart the work to the best of its ability and handing it out to other nodes. Okay. And let's see a slightly more complex interaction for PySpark, and that's, let's take a range of numbers, and numbers 0 through 10,000 here, or it looks like 100,000, excuse me, and let's ask our PySpark cluster to spread the data over the cluster and then sum up all the numbers, right? So it's going to do that map reduce operation that I spoke about before. You'll need to make a couple of small tweaks to this code here. Change that X range to range for me. Something happened along the way in the past few weeks, and now X range is not working. It looks like they upgraded to Python 3 interpreter underneath the hood. So I'm going to execute that, and it takes a hot second, but certainly it comes back reasonably fast, right? It's not going to be super comparable to what Python would do natively without any Spark at play, because Python natively has some pretty interesting optimizations, but still, you know, this is an impressive amount of speed for summing up these numbers, right? Especially for doing over the network communications. Number of slices just means the number of times to break down the data within the RDD. So number of chunks of the RDD to place over the nodes that you have. So let's say that you have 2 nodes. It would make sense to break up your data into at least 2 slices, right? The RDD will know how to slice and dice that data best most of the time. But if you wanted more control, you could say, you know what, I don't just want 2 chunks. Maybe I want 4, or I want 10, or I want 100. And so you can specify that with the number of the slices. In this next cell, I wanted to give you a little bit more of a deeper picture of the comparison between normal native Python and using PySpark, right? Because PySpark's not always going to be faster for a computation. If you need to just add 2 numbers, it's going to, and the 2 numbers are like 5 and 7, it's way faster for Python without any PySpark involved to just add those 2 numbers, because those 2 numbers are in the memory of the computer already. It's 5 and 7, right? They're in the master node memory. It would make very little sense to go out to another worker node, ask for 5, then come back with 5. You know, you're paying, in terms of time, you're paying for the transit costs over the wire between the master node and the worker node to communicate that. You do that twice, once for 5, once for 7, and then add up those numbers again. Like, no. That computation is much faster on one node. This cell shows you when that breakpoint starts to happen for at least this particular operation. And again, I'm going to replace X range with range. Okay. So I'm going to take these numbers. I'm starting off at that 100,000 that we had before, right? And I'm growing the numbers as time goes on. And I'm performing the computation in Spark as well as in Python. I'm going to just see, you know, which one's faster. So executing this cell the first time through, it looks like that, you know, Python is actually outperforming PySpark by quite a bit. It's like at least an order of magnitude, if not several, right? If we increase the order of magnitude of the numbers that we want to sum, though, then they start to be pretty comparable. PySpark is starting to show some gains, right? It's still a little bit slower than the amount of time it takes Python to add up those numbers. But as soon as we add in one more level of order of magnitude, and we're dealing with a sum of, how big is this? We're dealing with 10 million, right? So at the 10 million mark, PySpark is outperforming Python, right? And at the very last mark here, we're getting up into what is the 500 million, somewhere around there. Maybe that's 50 million, I'm not quite sure. It's clear that PySpark is faster, and it just gets bigger and bigger and bigger, right? The difference or the delta between those two performances. So the note that I want to make here is that PySpark is an excellent tool, but it's not always the right tool. It's really a better tool when you're working with very, very large data sets. I wouldn't take your, I wouldn't take your, HOA's information for managing, condominium costs and run it through PySpark. It's probably not going to be worth it. Excel or Pandas is best for that. But if you're working on HOA costs for all of the HOAs for all of the country of the United States, then PySpark might be your best bet. Cool.
Wait, Professor, question. Yep. What's the reasoning behind that lower time on PySpark at the second test you did? It goes from 1.7. Is that network?
What's the, yeah, this was startup time. If we run this again, we'll get a different number here. That's a good point.
Okay.
Does that make it a little bit clearer?
Yeah.
Yeah. Pardon for that. This was, the question was, why is this so much higher? And then this ended up being lower, but being a larger number that needed to be summed together. That was startup time for distributing this information over the cluster. Cool. So now we've created these ranges previously across the cluster by saying, hey, Python, here's all these numbers, distribute them over the cluster. Well, what if those numbers have a reasonable period to them, right? It's a normal sequence that we can analytically define rather than numerically define by passing through the numbers. Range is one of those, right? Any computer can figure out range. We don't need to figure out range on the master node and then push it to the worker nodes. So that's what this line here does. It says to the Spark context that, you know what, I want a range from 0 to n to exist, and I want you to push that down to the worker nodes. Have the worker nodes determine for themselves what the range is that they're responsible for without them needing to receive those numbers, right? And again, I said 10 slices just to play around a little bit more. I'm going to do that same map operation. I'm going to, well, not the exact same one. I'm going to do an equivalent map operation. I'm pushing down this Lambda function to each worker node. I'm going to say, you know what? I want you to find the square of all of your numbers and then sum that. And the worker node will then reduce the results that each worker node finds. And this takes, takes a reasonable few seconds, but you'll eventually pop out an answer.
Professor, so for this cell, I got a different answer than the second cell. Oh yeah, like are these supposed to be different? Because the n is the same, right? We didn't change n.
Did you get, are you saying you got a different number than this number, or you?
Yeah, I have the same as your your number.
Okay, so if you had a different number before, you may have just run this cell before you ran this cell. So this cell is working off the latest version of n, which is this 500,000 or what is it? Let me just put in some. It's 50 million, right?
Oh,
so it's working off. Go ahead.
Oh, sorry. It's just like for n, so the n in the for loop updates the value of n. I thought it's just in the for loop, it's kind of like for I in range, let's say like in range 10. I thought that only works like during the loop. Does that modify the value of n in the global frame?
Yes, yeah, so I understand the question now. N is this last number that came through the loop. So if we do this, we get that 500,000 or 50 million.
Okay, I see.
If we didn't evaluate the cell, then N would still be this 100,000.
I see. I see. So what's the difference between like using parallelize versus sc.range without the parallelize?
Sorry, 1 second. Okay. What's the difference of using parallelize without using parallelize?
No, so the second cell we use sc.parallelize, and then the range in the parentheses. But in this, yeah.
Yeah, okay. So in this case, where is the sequence being created? Where is the number sequence being constructed and potentially, we're potentially asking for memory to hold the contents of this range. Where is that being done? What's being done on the master node, right? So the master node is going to create all the numbers in between 0 and right? Maybe 50 million, right? And then it's going to take and start pushing down bundles of those numbers to workers, right? So there's a whole lot of information transfer between the master node and the worker nodes. There's also a whole lot of information creation on the master node when it's not necessary, right? A worker node could figure out what its numbers or what numbers it's responsible for in a range if it just knows that, hey, I'm node 3 out of 5, and the number sequence range for all of us is 0 to 10, right? If I'm 3 out of 5, then I know I'm responsible for 1/5 of the numbers, and I know that I'm node 3, and I know that the sequence of the numbers starts at 0, goes up to 9, right? So that must mean that I'm responsible for 4 and 5. I'm responsible for numbers 4 and 5 and doing whatever operation between that set of numbers. Does that make sense why we might want to use sc.range over parallelize?
Sorry, I don't quite understand. So we have to do parallelize first to let the nodes know which number to process before we do the range, or
no?
Yeah,
so parallelize is used to ship information down to worker nodes if the worker nodes can't figure that information out for themselves, right?
Okay.
So if they don't know about the sequence of numbers or they can't figure it out, which would kind of be the case here for 4, 10, 9, 7, right? There's not really a clear pattern in those numbers, right? So you're going to need to parallelize. You're going to have to push those numbers to the workers because they're not going to be able to figure them out. For a range, though, a range is just 0, 1, 2, 3, 4, all the way up to 9, right? So we're going to say, hey, worker nodes, your worker node 3, I want you to take on 1/5 of the numbers, figure out what numbers you're responsible for. I'm not shipping them to you. And so now we save on all this network bandwidth, right? Cool.
Okay, so it's just the we can use so we don't have to use parallelize if we have consecutive numbers, but if we don't have consecutive numbers, we need to use parallelize to kind of assign the work. Is that kind of a generalization?
Exactly. I would say generalize it even further. If the worker nodes can figure out the data for themselves, then we can use some other method on the Spark context. We don't need to use parallelize. Parallelize is specifically for pushing information down to the nodes that they don't already have.
Okay. In what other situations will the node already know which instances they are responsible for?
Right. In the most simplistic cases, you could just say any other formula that's easily written out in terms of a Python function that can be pushed down, right? But in I think a more practical sense, you could have those other nodes, the worker nodes, know where a file exists or where a set of files exists, And then they could go and figure out, okay, which files am I responsible for reading, and I'll do that reading. That would be much better that your worker nodes read the files themselves than the master node read the files, right? Read all the files and then push down the information in those files to each one of the worker nodes, right? It'd be so computationally inefficient if it were to be done the second way. Does that make sense?
Yeah, that makes a lot of sense. Thank you.
Yeah, cool. All right, so we're going to do another parallelize operation. Where is this Jupyter Notebook saved? Bucket or the cluster of VMs? It's saved in the bucket, but it's being run and executed on the master node. Cool. sc.parallelize, I'm going to push down this range of 5 numbers. I'm going to push it down into 5 slices. And this cell, what I want to show is how do you collect information back out of all of those. If you're not doing some sort of reduce operation, right, which you are when you're doing a sum, right, or maybe an average or mean, something like that. When you're not doing some aggregation, sometimes you just want to pull back the numbers. And the way you can do that is with glom. Glom collects per partition. And these partitions, these are those slices that I was talking about before. When you were creating 10 slices, we had 10 partitions underneath the hood. And again, partition is just like this kind of subcategory of data structure that you really don't need to worry about most of the time. You just need to know kind of how to get past it once you're at a point where you want to aggregate your information. And so glom will go fetch the information. Well, excuse me. Glom tells PySpark that you want to grab all of the different partitions worth of information, and then collect will actually do that collection operation. It'll instruct PySpark, okay, go ahead and do that, actually do the fetching from each partition. And so here we get back a list of lists, and in each one of these lists, it's a partition's worth of information. We have 0, 1, 2, 3, 4, right? If I put everything into only one partition, only one slice, then when I did my glom collect, I only get back that one partition. Again, the only reason I mention this now is just so that if it catches you off guard later on when you're working with PySpark, below the layer of RDD is this concept of partition. It's a logical concept in a lot of ways. And it's just another way to kind of bundle the data together so that PySpark can make its computations a little bit more efficient. Okay, so this is the very basics of PySpark. It's just enough to get us into this next example that I want to run through, and that's the Titanic example. So oftentimes you're working with Dataproc to look over a bunch of data and do some sort of machine learning operation. Certainly not the only reason you'd use Dataproc, but it's the category of operation that I see used most often for. So let's update our notebook first before we go much further. This is a generic Google storage string, gs://pdl dataproc. I want you to update this to your bucket name. Okay? So my bucket name is this here. I'm gonna go ahead and grab. Oh boy. Let me go over here. Go back to cloud storage. Okay, it's PDL Dataproc 2021 fall, blah, 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 blah. And I'm going to replace that value in here. No spaces on either side. Don't want that. And also, if you didn't put train and test in a Titanic subdirectory, then you'll need to change this path to use the correct subpath for your train and test CSVs. If you click on the CSV itself in your data bucket as a link, you can just copy. Oh, okay, yeah, there you go. Yep, there you go. All right, so we're going to execute this first cell. It's going to take a second because it's reading over the wire. We're also specifying the header to be true. This tells PySpark to read it as a CSV file with the first row being considered a header, and to infer some schema, i.e. try to take your best guess at guessing the data types for each one of these columns. Okay. And it does a pretty good job. You can see that we got passenger ID here is an int, survived as an int, passenger class or P class is an int, other things are strings. So yeah, it makes some sense that PySpark did some of the work for us. If you want to, you can take a look at the structure of the files, but these are all files that I pulled down from the Kaggle exercises, that website for doing data analysis exercises. And in that data, you'll see that there's a bunch of columns, and the test or the goal of that data exercise is to see if you can make a pretty good prediction for who's going to survive and who's not going to survive in Titanic. A little bit morbid of an example, but who's going to survive based on some of the attributes that are also contained in the CSV, right? Again, you have things like passenger class or age or sex or things like that, right? But we're going to try and do the same thing, but we're going to do it with PySpark. Because PySpark uses the functions attribute so often let me rephrase, because in this particular set of data analysis, we use the PySpark.sql.functions operations so frequently, we're just going to import it as F. And oftentimes you're going to be using this library and this set of functions if you work with any type of relational data. So you'll often see this is just at the top of your notebooks. I'm going to execute that cell, import that. And I'm going to do my first operation, which is I'm going to rename survived to label. And this is because I'm starting to try and restructure my information in a way that's easy to hand off to PySpark's and Python's internal machine learning libraries. And what they usually like is they like a set of columns or a single column called something like features. And then they have another column called labels. And it's so long as your data frame has those two columns, it can have others, it doesn't really matter, but as long as it has those two, the library will look at those two and do its machine learning operation on those two, right? It's going to try to come up with the best fit model between the two. And so I like to start off by renaming columns appropriately to get some of the grunt work out of my way. Okay? And if I was to just do this first line in this cell, this with column renamed operation, PySpark wouldn't do anything. PySpark would just say, okay, this is part of my to-do plan, right? Because remember, PySpark is as lazy as possible. It's trying not to do operations until the very last second. But because I did this df.show operation, I get the first 5 rows of my information back. So now it's forcing the workers to hand back some information to the master node. Okay. Now I'm going to do my second operation here. I'm going to try and transform age into something a little bit more workable for a machine learning model. If you look through the age column, you'll see that some are null. And while null is workable in machine learning models, it's better if all the values in a particular column are of the same type. They're either integers or they're all not strings, but they're usually all integers. In some way, shape, or form, we want to get all of our information into an integer format. If something's null, that throws a wrench in the gears. So let's get rid of that. And we'll do that by looking through this column age, and we'll ask it if it is null, right? That's what this bit of code is doing. If this turns out true, then I'm going to replace that value with -1. So that's what this fwhen operation does. So these are our first 2 examples of the methods that are attached to the functions library. Call will look up a column and look up attributes on that column or look up qualities of rows in that column, like is it null? And then when will do some sort of like if-else computation for us, right? What we're building out here is called a DAG, or a directed acyclic graph. Okay? The directed acyclic graph is basically just a set of sequences that we're going to perform on the information to eventually get a result, right? PySpark is optimized to take the best path that it can through a DAG, so that, again, like I said, if there's two steps that cancel each other out, you might as well just not do those two steps at all. On the end of a when operation, you can add this otherwise. So that's kind of the else clause of your if else statement. So if it's not null, then let's keep age as it is, because that's a valuable number. We want to hold on to that number. Okay. That could be a valuable predictive entity. And again, I'm going to execute this. Again, if I had only created this first line, Python would have not done anything except for, or PySpark would have not done anything except for add to the DAG. But because I did df.show, it executes the DAG and shows me the first 5 rows. And it looks like age, didn't have any changes, but I guarantee you, wherever there was nans in that column, they are now replaced with -1s. Okay. And when I say nan, it's an equivalent of null. Here, we change out the sex class, right? So right now, sex is either male or female, right? We don't want that. We want it to be, well, although this might not make sense for all the scenarios here, we want it to either be a 0 or a 1, right? For male, we'll say that's a 1. For female, we'll say that's a 0. Again, we're trying to convert this string information into an integer format. Okay? I've spread out this when clause, or this longer stringed if else statement, into 3 chunks. So when the sex is male, go ahead and replace that with a 1. When sex is female, replace it with 0, otherwise -1. And I'm doing df show at the end. Now, when I'm working on a PySpark DAG like this, I will use df show quite often. I'm checking my work as I go, right? When do I get rid of the show? When I productionize it. So when I take out, when I'm ready to put this into a continuously building model, something that's going to continuously rebuild the information on the fly and rebuild a model time and time again, then I'll remove the shows and I'll just string all of these df operations together. Okay. I rename it as df so that it's as simple as just commenting out the df show, and then one df will take on the next df's value, and it'll be implicitly stringed. Okay. Now, embark is a little bit tricky. We don't know how many different values we have in embark. We know that, or embarked, I should say. We know that S and C are values, but what are the other values out there? And so that's where we'll take df and we'll select on embark. We're using kind of SQL syntax here, so we're calling it select, right? And then we're going to run collect to actually run that select operation, right? To force it to give us the values. We're going to pass that all to a set so that we can get the unique values in the column. And we can see that there's 4 unique values. There's C, Q, S, and none. Okay. We'll pass those into another F when, when otherwise clause. And we'll see if that worked out on the right-hand side. And sure enough, it did. Now we've got another set of numbers to play with, which is great. We're going to do similar operations for fair and for cabin. Okay. Cabin's a little bit more complex because cabin can be, if you take a close look, it can be prefixed with this uppercase letter and then a number. There can also be nulls. So, I wanted to build out my machine learning model such that the first letter, that's the prefix of the cabin, right, could have some intrinsic value or some predictive properties to it, separate from the number that's associated with the cabin. So maybe if you were in C1, you had a less likely chance of surviving than if you were in C123, right? So I broke apart those values and did so like so, right? So I lowercased the values, then I asked the substring for I ask the cabin for its first value. It's the substring of 1. I cast that substring to a number via an ASCII operation. If you're not familiar with ASCII, it's just the, I don't want to say oldest, but it's one of the oldest and most long-lived number to letter mappings that's out there in the world. So again, I'm just trying to get towards a number for this, this cabin value. And then I asked, well, is the cabin null? If it's null, let's replace it with a -1. Otherwise, let's use this new ASCII value that I've created for cabin. And let's see what that looks like. I didn't add in the value of the cabin number just yet. You're free to do that on your own, though. I left that as an exercise for y'all if you want to take it on. It's just one more line of code here.
I have a quick question.
Yeah.
So if you do the substring 0, 1, you get the letter, for example, like C, or like maybe there's a B or an A. And then when you do like ASCII, like ASCII on the cabin, are you doing it for the whole like letter plus the numbers? So you do it for like the entire C1, 2, 3, or how does that work?
No. So yeah, let me back up to make sure this is clear here. Lower is going to grab the whole string that makes up a cabin identifier, right? So it's going to take C1, 2, 3. It's going to change it into lowercase C1, 2, 3, right? And then the substring operation is going to take the first letter or first character from that string. So it's only going to take C, and it's going to specifically take the lowercase c. Okay? Then I'm going to pass that to ASCII, and ASCII is going to convert that lowercase c into a number. Okay? Only the lowercase c. It's not going to take 1, 2, 3. And then once I have that 1, 2, 3, or excuse me, once I have that number equivalent of C, which if it's lowercase, it's probably somewhere around 65. Okay? No, sorry, 99, probably like 99. Then we're going to take this cabin value, right, and ask it, well, are you null or are you a ASCII number? If you're null, I want you to replace yourself with -1. If you're the ASCII number, then just stay the ASCII number. Does that clarify?
Yeah, I think when you just said, for example, if you are in a C123, you might have a better chance to survive than C1. So I think based on like your that statement, you should compare the numbers instead of like C, right? Or do you mean like if you are in C, you probably have a different chance of survival than probably you're in A?
So right now, my machine learning model that I'm building out is only taking into consideration the class of the cabin, right? So whether it's A class, B class, C class, what have you. I made mention of the fact that there might be different properties in between, you know, the C1 and C123 cabins, so that I could preface that you could add in that extra bit of line of code yourself. That's left as an exercise to y'all if you want to do that. Okay.
Okay, got it.
Yeah. Could I have left, could I have left the C and 123 stuck together and come up with some number? I don't. You can't really do that. You need to separate those values out because they're really two dimensions stuck together, and you need to separate those dimensions out, or you're going to get like garbage junk going into your machine learning model. Does that answer your question?
It should be 2 columns if we're to separate them out.
It should be 2 columns, yeah. And that's kind of a hint for the line that you need to add here in this cell. Okay. And then Alexander, it's 99, it's on your screen, but why do you have, you work long enough with ASCII, you're gonna memorize some of it. Cool. So now that we have some cleaned up data, certainly not as cleaned as we could, but we have some amount of cleaned data, we can pass this into a machine learning model, right? machine learning models like to ingest numbers and spit out numbers. So we've got a nice set of integers and floats to work with to pass to them. We're going to specify the columns of information that we want to pass in as our feature columns, i.e. that set of columns that will be able to have predictive power over whether or not the passenger survived. It's going to be the total set of columns minus passenger ID minus label, right? Of course, we don't want to predict whether or not someone survived based on the survived column, right? Defeat the purpose. We are also not going to take into consideration name or ticket. Okay? And so that's what that does here. I can actually show you what those columns look like there. Okay, so those are the columns we're taking into consideration. All of these other columns that we didn't perform an operation on, they should already be integers or floats. And then we're going to do this kind of nasty bit of junk, right? We are going to import vectors and vector assembler, and we're going to build a features column out of the feature calls that we have and out of the data frame that we have. This is, in my opinion, this is kind of a wart on the machine learning libraries that are built into PySpark. It's much more cumbersome than, say, when you're dealing with scikit-learn. Scikit-learn is smoother around the edges. You don't have to do as much of this importing and building abstract objects to get the job done. But at the end of the day, this features value is just another vector. Okay? It's another item within our data frame that represents all of the features that we had in these other columns. It's duplicating information, but it's duplicating it in a way that it's easy to hand off to our machine learning model. Okay. So now, because we're doing good machine learning practices, we're going to split our data up into two chunks, some training data and some testing data. Okay. I'm doing a 70-30 split here. I'm using some seed 218 just for consistency's sake, but you could leave the seed empty if you wanted. And yeah.
Yeah, so for the vector assembler, if our input columns are the selected columns from that we just did, then but we transform it on the entire data frame, does that mean we're only modifying the feature columns and then we're leaving passengers, passenger ID, label, name as it is without transforming it?
Even more than that. So what vector assembler does is it just looks at these feature columns and creates a new features column. I know it's confusing, the words are identical, but it's going to take this set of columns that we've defined as our feature columns, the columns that we think have predictive power. It's going to look at those and create a new amalgam column, which will be entitled features. You'll see here down at the very end, it's a vector column. It's not an int, it's not a string, it's not a double, it's a vector, right? That's what this vector assembler does. It does not change, it does not change the rest of the data frame in any way. Does that answer your question?
That makes sense. Thank you.
Yeah. Okay. Now we're finally to the point where we do, I'm sorry, everyone, I'm on call today. And so I'm kind of needing to tell people to silence for a second. Sorry. So now we're to the point where we actually do the machine learning, right? We've built up all this, all this information. We've moved the whole way through all of this cleaning so that we could do this one cell right here. It's this cell that actually does the machine learning. And we're going to use a random forest classifier. Why? Because it was the first one that I thought of. You know, I encourage you to try other classifiers and see what kind of better fits that you get. It's an easy one to start with, and it's kind of fast. So it'll run in the background. I didn't have to change the data frame in any other way because I've labeled the survived column as label, and because I've labeled that features column as features. I just have to pass in the train and test data off of the features to the classifier. It does it, you know, I get results, right? There's no extra column information that I have to pass to these methods to get it to work right. And if I take a quick look at the ROC, then I get a reasonably high number, you know, 0.85. So that's nice, you know. That's always not the only number that you want to look at when you're building out an ML model. But it's nice that on a first whack, we got such a good association between our data and the result, right? Maybe we overtrained a bit, who knows? So now in this next cell, what we're going to do is we're going to test with our test data set. So when we trained our data set and you know, created a test data set to train with, that was all based off of that that was all based off of the train CSV. Now we need to train, when we did all of our machine learning model, we were working with the train.csv, right? And we split it up in fractions so that our machine learning model could run. Now we need to test whether or not our machine learning model is really producing, you know, accurate results with the rest of our data, that test data set, that test CSV. So let's go ahead and get the name of the bucket and update it here again. I'm gonna go up to the top of the cell.
Can I ask a question? So
yeah,
like for the random forest classifier, we just use like fit train. You mentioned that because we have a column named label and a column named features, that's why like they know our like X train and the Y train. However, if we kind of change the name to like maybe capital letter F like feature and then like capital letter L for like label, can it still recognize it, or like versus like labels? Like how can it? Oh, okay. I see. So it only recognize like features and labels.
Yeah, and you can override this with other keyword arguments. You could say, you know what, don't use lowercase features. Use this other column for your training operations. But I personally like to just stick with what's easiest. I'll rename the stuff, and I always know that my stuff is labeled under the features column. Like I always know that my predictive features column is labeled features. That's just the way I roll.
I mean, like if you don't specify, so like features is a data frame with a lot of columns. It happens so that one column is a label and one column is the features, like feature vector, right? Features like vector. But like when we fit it into a model, how does it know, since there are a lot of columns, how does it know that it should look at features as the training X and then the labels as the Y for training? Yeah,
good question. That's just how vector assembler works and how these train and fit operations on the classifier work. They first default look for this column.
Okay, and for labels it's the same. We cannot
exactly
name it like label without an S.
Again, you could. You just need to make adjustments to the rest of your code. And it's not the default, so you're going to have to add in extra labels like this, like a classifier fit train. I don't know what the keyword argument is off the top of my head, but you'd have to do something like label equals, you know, whatever you named your column, my label call. Does that make sense?
Oh, okay, makes sense. Thank you.
Yeah. Cool. So now we're going to do the exact same operation that we did up above before. We did all of this operation once. We're going to do it once more. I got rid of the shows in between, and we're going to now run this on test. Okay. And we get predictions out. Now, finally, we will print out. Oh, sorry. When I said test, what I meant was the test CSV is the test CSV that we were going to use with our submission to the Kaggle exercise. So here, if you jump into the Titanic data set, you'll be tested on your submission of a test CSV, right? So they give you a test CSV, it doesn't have survival information on it, and you do your best at coming up with survival results for that test CSV. Sorry, I misspoke there before. And so that's what this cell does. Okay. And I'm going to rename the column from prediction to survive, because prediction is the default column that is made by this, this operation. I'm going to write those predictions back out to a CSV, and I'm going to do this. Okay. And I'm going to do this. Again, I'm just renaming that bucket name, that default bucket name. Okay. So I write back out. Takes a couple of seconds. It's writing over the wire. Okay. And if we go back over here, we see we now have this results bucket or results folder. And even though it was supposed to be a CSV file, it still pops out as this nested CSV file, which is, it's not that great. I don't like that interface, but still it works. If you were to download this, then you would get these nice columns of information of passenger ID and whether or not they survived. If you upload this to Kaggle, you'd see that you'd get, at least when I ran it, I got somewhere around like a 76% predictability. So, it's not great, it's not perfect, but still pretty darn good for very minimal data cleaning and the simplest of machine learning models, right? Random forest. So that's how to run PySpark, right? It was kind of a whirlwind. We jumped through first, how do you spin up a PySpark cluster? We then talked about how to do some very basic PySpark operations, like distributing information over your worker nodes and aggregating them in some way. And then we did this machine learning exercise where we tried to come up with predictive results or correct results, predicting the survival of different passengers on the Titanic. And we did it all in PySpark, right? So without further ado, I'm going to leave it open for a little bit of questions and then hand it back to Liz. Could you combine PySpark data cleaning with scikit-ml? You prefer that package? Yeah, you certainly could. It would. I wouldn't, unless your resultant data, that's your cleaned data, is small enough that it makes sense to do that, then I think you're probably still better off staying in PySpark. PySpark is really designed for working with this huge chunk of data, right? These really large data sets. If your aggregation, your map reduce operations and your cleanup operations produce something that's small enough in size that it can be run by a reasonable sized node, maybe that's 96 gigs of RAM or something on the cloud or whatever, but something that can fit on a single node, then yeah, maybe it makes sense to do all of your ML in scikit. But if your data still persists in a large state, then you're kind of stuck with PySpark. And so I usually just don't even think about going back into scikit-learn. So.
Professor Lockton, I got a couple questions in the chat about the ability to sort of revisit some of this. So I know we're not distributing the recording, but can you confirm from your GitHub they can get to the slides? Can they get to this Jupyter notebook if they want to go back and revisit some of this?
Yeah, so data proc. So here's the public repo. You can go to this, and then here's the slides in the README. So you just have to flow through these slides and, excuse me, these slides are the slides that we went through here. So if you have questions about that stuff, then the information's there. But if you wanted information from the notebooks are just in the repo itself. It's not in the README. And you can run through these. Cool. I encourage you to continue to tinker on the cluster if you have it, and then shut it down, save your money, and try it again and again, or try something else on GCP. $5 can get you quite a far away. A week's worth of compute power to just play around on GCP. So it's a fun resource to have. So. All right, everybody. Well, thank you. I hope you enjoy the rest of your Friday and go play with some big data.
Thank you so much, Professor Logsdon. Thank you all for being so participatory in the chat, on mute with each other. I always love to see that. It's a quick reminder, PDL feedback email coming Monday. So if you don't see it this weekend, do not worry. And if you enjoy hanging out with Professor Logsdon on Friday afternoons, we are taking next Friday off. It is Thanksgiving. But the first week in December, we are doing ethical hacking. And then December 10th, we are doing deployments. So if any of those things sound cool to you, they will be in the forthcoming PDL elective emails. So keep an eye out for those. But thank you all. Thank you, Professor Logsdon. Have a fantastic weekend, everyone. And remember, short week next week. We just got to get through 2 days. Thank you.
All right. Bye, everybody.
Bye, everybody. Any PDL questions?
Thank you.
Let me know. I'll hang out another minute. There's one in the chat. There is no limit on the number of PDL sessions you have to go. There is no upward limit. There is a minimum limit in that you got to go to at least those 5 electives, including 1 interview and 1 life management. There is no upper bound. So if more than 5 are in interest to you, please come. We're always happy to have you in class. And those will continue. We'll have lots more stuff in the spring also. Awesome. All right, I'll hang out another minute in case there are PDL questions or anything else I can help with. But we are wrapped up, so if you drop off now, you are free to do so. That is correct. 5 across your first 2 semesters in your program. So if you see 5 that you really like in the fall, great. We will keep you on the email list for 2 semesters no matter what. So if you finish your 5 in the fall, you'll still get those invitations in the spring. Okay. All right. Well, if any questions come up after we get out of here, PDL-Cs, Gabby and I are on it. Happy to hear from you if there's anything we can do to help. All right. Have a fantastic weekend, everybody. See you next time.
Hello, this is Chef John from foodwishes.com with butter chicken, turkey, and gravy. That's right, we're gonna make an Indian butter chicken inspired roast turkey, which I thought was a great idea, and it was. And by the way, this technique's gonna work no matter how you like to prep and roast your turkey, which is a good thing, since what wasn't a great idea was the yogurt marinade you're just about to see. But all's well that ends well, and this ended very, very well. So what I did first is mix up a marinade using plain yogurt, some ginger, some tomato paste, some garam masala, some smoked paprika, some chili powder, some ground cumin, some salt, some turmeric, which prevents almost every disease, some ground coriander, some garlic powder, and then last but not least some cayenne, which prevents all the other diseases. And once all that was together, I went ahead and gave it a mix and set it aside. And I moved on to prepping my turkey, which usually always starts with me sticking my fingers under the skin. And no, not just because it's fun and freaks out everybody watching. It's because I want to loosen that skin so I can get a spatula underneath. Because whenever we're going to roast a turkey, I think we always want to season it under the skin and not just on the top. And even though we can only do this over the breast meat, that's still a lot of surface area. And I really do think this technique should be utilized no matter how you're going to do your turkey. Okay, I really do think this makes a big difference. Although what I usually use as a base for my salt and spices is butter. So as I spoon and spread this marinade under the skin, I want you to pretend it's soft butter. Because if you do this, that's what I think you should use, which I believe we've done in all our previous roasted turkey videos. But anyway, what I did was spread like 3 big spoons under the skin over each breast. And then once I had that breast meat marinated, I went ahead and spread the rest of my marinade over the entire surface. At which point my plan was to pop this in the fridge and let it marinate overnight. Which again, with a seasoned butter is a fantastic idea, but the yogurt was not as successful. But since this was inspired by butter chicken, I wanted to try the same first step, where the chicken is marinated in yogurt and then grilled, and then finished in that amazing creamy tomato curry sauce. So that's my excuse. But the important thing to remember is from this point on in the video, no matter how you've prepped and seasoned your whole turkey, the rest of this method is going to work wonderfully. And that's it. Once we have it fully prepped, nicely seasoned, ready to roast whole turkey, we can move on to the rest of the procedure, which I thought worked brilliantly. And that's going to start by placing a roasting pan over medium heat and melting an entire stick of unsalted butter. And if you're wondering if you can use margarine, please turn off the video. And once that butter melts, we'll go ahead and toss in some ginger and garlic. And what we'll do is give those a stir with our spatula and sizzle it in that hot butter for about 30 seconds or so before we add our spices. And those will include some chili powder, preferably Indian, some garam masala, some cardamom, a little bit of ground clove, and then the only semi-exotic spice you might have to hunt for, some ground fenugreek, which provides one of the signature flavors of butter chicken. And we'll go ahead and stir all that together and cook those spices for about 30 seconds to a minute to sort of toast them in that hot fat and wake up all those flavors. And at this point, your kitchen will be smelling amazing. And as soon as it does, we will stop and add our diced onion. And we will saute that for a couple minutes until it just starts to soften up. And by the way, if you don't have a big roasting pan and have to use one of those foil ones, don't worry, just do all this in a big frying pan and then transfer it in. And this will all work exactly the same. I mean, you are fairly Steely Dan of using a non-Steely pan. But anyway, once our onions have started to soften and sweeten, we will stop and transfer in some crushed tomatoes. An extra credit if you're using the fire roasted variety, which again is a nod to the original butter chicken recipe, which usually features char grilled pieces of chicken. So that little bit of fire roasted smoky element is very nice in this. And we will stir all that together and wait for it to come to a simmer. Oh, and I think we also want to add a nice big pinch of salt here. And of course, we will adjust our seasoning in the final sauce. But I know we're going to need a little bit. And that's it. Once the base of what will eventually become our curry sauce has come to a simmer, we'll go ahead and remove that from the heat. And we will carefully place our prepped whole turkey over the top, which again can just be a whole turkey you've simply seasoned, which is what I wish this was. And then before this goes in the oven, we have to tuck our tips. Oh yeah, as you might know, my biggest Thanksgiving pet peeve of all time is people roasting their turkey with those wing tips sticking up, which I think is very unsightly and borderline obscene. And yes, we should probably fold those under before we place it on the hot sauce. But that's how strongly I feel about needing to tuck the tips. I was willing to risk burning myself to do it. And then the only other thing I like to do is tie the two legs together, which some people say makes us cook more evenly, but really it's mostly for appearances, I think. And that's it. Our turkey is now ready to roast in a 325-degree oven for about 3.5 hours, at least for me for this size bird, or until it looks like it caught fire in the oven. Oh yeah, that is stunning. And not stunning beautiful. Like stunning as in I'm stunned and I don't know what to say. Although I'm guessing there's some people out there that actually think this looks good, since no matter what something looks like, there's someone out there that thinks it looks good. And kidding aside, while it was very dark, the appearance was not the main problem I had with the marinade. Okay, it was actually a textural thing. But we'll get to that later. For now, we're going to remove that from the roasting pan, and we will let that rest while we finish our amazing butter chicken curry sauce inspired turkey gravy. Before that, we will transfer everything from the roasting pan into a saucepan, which I won't make you watch. But once we have that all in there, we'll go to the stove, and we will set that over medium-high heat. And we will thin that out a little bit with some turkey stock, which we've obviously made with the turkey neck and giblets and have simmering on the stove somewhere. Or just use some prepared broth. And we'll also go ahead and add our heavy cream. And if you don't do dairy, this is really good with coconut milk as well. And what we'll do is give that a stir and wait for it to start simmering. And while I was waiting, I went ahead and added a spoon of sugar, just to sweeten things up a little bit, and hopefully balance things out. And some people like to use honey, so if you're into that, that will work. And I don't like this too sweet, so I'm only gonna add a little bit, but you need to do that to taste. And then what we'll do once this is bubbling enthusiastically is let it cook for about 5 minutes, during which time it's gonna reduce slightly, not to mention start tasting absolutely amazing. So other than adjusting with some salt, we should be okay on taste, but we need to finish the texture, which means blending this very smooth. So what we'll do is remove that from the heat and blitz that with our immersion blender. And by the way, as soon as you remove that from the stove, you're gonna have a whole bunch of melted butter floating to the top, but do not under any circumstances skim that off. Okay, we're calling this butter chicken turkey, and it would be nice if we meant it. And you'll see as you blend this together, all that butter's gonna get emulsified into that tomatoey creamy goodness, providing just an absolutely gorgeous, luxurious mouthfeel. And then we could strain the sauce if we want, but that's optional, and I'm not going to. But what's not optional is that we need to taste this and adjust the seasoning if we need to. But I'm happy to report mine was perfect. So I went ahead and sliced off a piece of my stunning turkey and ladled some of that sauce over the top and went in for a taste. And above and beyond the turkey's visual challenges, the real reason this marinade didn't work is because that yogurt marinade, especially since it was on that breast meat for so many hours, gave the meat a little bit of a weird mushy texture. Okay, it looked dry, but it wasn't really dry. It was just sort of soft and chalky. And also, if it's on there too long, turmeric can have the same effect. So I think that was partially to blame as well. But luckily, that was only the case for like the first quarter or half inch down. And as I cut some nice bigger slices and plated up, it really was not that big of a deal. So to summarize, do not use that yogurt marinade, and maybe go with a flavored butter instead. And again, refer to our old turkey videos for that technique, as it really does work beautifully. And then, since this was inspired by butter chicken, I garnished with some sliced red onions and cilantro, which I thought would help cut through the richness of what turned out to be an amazing, truly memorable sauce, which I will refer to as a gravy for the rest of the video. And what I love so much about this, all those beautiful juices and drippings coming off our roasting bird were being absorbed into our gravy ingredients underneath, which really did take that flavor up to a whole other level. And while certainly not traditional, this was one of the best turkey gravies I've ever had. And of course, I made sure by giving it the old mashed potato test, which it passed with flying colors. Speaking of which, not to diss regular turkey gravy, but I thought the deep orange color of this was extraordinary. And as far as flavor profiles go, I think this is going to work very nicely with all those traditional turkey side dishes. So we got that going for us, which is nice. And by the way, the dark meat fared way better, so that marinade actually would have probably worked out well if we had just done dark meat here. But for the holiday, we really do want a whole bird, I think, which is why I'm recommending a little more standard prep on the turkey. But anyway, that's it. What I'm calling butter chicken, turkey, and gravy. I tried something new, and while the first step didn't work out as I'd hoped, I thought the rest of the method was magnificent. And if you like Indian-style butter chicken, or curries in general, I really do hope you give this a try soon, except for the yogurt marinade part. So please follow the links below for the ingredient amounts, a printable written recipe, and much more info as usual. And as always, enjoy. Hello, this is Chef John from foodwishes.com with lemon pepper sweet potato crisp. That's right, I am very excited to be sharing my new favorite sweet potato side dish, and I can't decide what I enjoyed more, the incredible textures or the amazing flavors. So I'm gonna call it a tie, and there's no winner, which is fine since everybody loves a tie. All right, I think that's why soccer's so popular. But anyway, this was truly fantastic. And to get started, the first thing we need to make are some extra large breadcrumbs, which we really can't buy, so we're gonna make them ourselves. So I'm gonna go ahead and take this hunk of bread and cut off the crust before we slice this up. And the reason I'm trimming off the crust first is because crust does not crumb. Okay, basically always stays as crust. And I want something here that's gonna be able to crumble. Plus the crust is already kind of dark, and by the time we're finished with this dish, those pieces might be too dark. And then once our bread's been uncrusted and sliced into thin pieces, we'll go ahead and turn it and cut it across like this. And don't worry if you have a few bigger pieces here and there, because as you'll see, we're gonna crumble this a little smaller as we apply it to the top of our sweet potatoes. And then once that's been accomplished, we will transfer that into a bowl, and we'll go ahead and pour in some melted butter, along with a nice big pinch of salt, plus a few shakes of cayenne, just to stay in shape. And then we'll finish up with a handful of grated Parmesan. Oh yeah, the real stuff, Parmigiano Reggiano. And once we've sprinkled that in slower than we need to, we'll go ahead and take a spoon and mix this all up until it's evenly coated. And then once we feel like that's definitely happened, we will transfer this to a silk pad lined baking sheet, and we will arrange that into some kind of uniform even layer. And then what we'll do once we have that arranged as shown is go ahead and sprinkle over our second cheese, which is going to be some grated sharp white cheddar, and we will sprinkle that over the top as evenly as we can. And in case you're wondering, why didn't we just add the cheddar when we added the Parmesan? Well, that's a good question. And the reason is that finely grated Parmesan will actually stick to those buttered pieces of bread, whereas the larger, heavier grated cheddar will basically just fall to the bottom. But using this method, it's going to go over the top and melt down and into that bread once it goes in the oven, which is the next step. So once that's been cheddared, we'll go ahead and pop that into a 375-degree oven for about 20 to 25 minutes, or until it's a beautiful golden brown and looks like this. And even though this stuff is pretty crispy right now, as it cools, it's going to get even crispier. So all we need to do at this point is let it sit while we move on to prep our sweet potatoes. Oh, and while it's cooling, do not do this or that, because once you start, you can't stop. So we'll just leave that be, and we'll move on to cut up some sweet potatoes, which as you can see have been peeled. And when they're this big, I like to cut them in thirds. So I have 2 pointy ends and then that large section in the middle. And we'll go ahead and have those end pieces using kind of a rocking motion with the knife, since sweet potatoes are very dense, so you want to cut carefully. And then once that's done, I'll go ahead and cut one piece off the end like that. And then the next piece we can cut into 2 or 3, depending on how big you want it. Speaking of which, I don't really care how big you make these pieces, as long as they're all about the same size, which of course is so they cook evenly. And then as far as that larger middle section, we'll go ahead and have and quarter those. Or if they're really big, you can cut them across in 3 pieces. But bottom line is we're going to try to match the size of the first ones we cut. And then what we'll do once we safely and carefully cut everything up is go ahead and transfer those into a mixing bowl. And then what we'll do once we have those bowled up is grate over the zest of 1 lemon, after which we will cut that in half and squeeze in the juice. And of course, when you see a recipe that calls for the zest and the juice, always zest first and then juice. And if you're not sure why, try it the other way around. Okay, it will be significantly harder. And yes, lime would work here as well, but lemon and black pepper go so well together, that's why I go with the lemon. But anyway, after the juice is in, we'll go ahead and sprinkle in some more salt, as well as a very generous sprinkling of freshly ground black pepper, plus a few more shakes of cayenne, just to stay on brand. And then last but not least, we're going to finish this off with some melted butter. And then what we'll do is take a spatula and toss this until everything's evenly coated, at which point we can transfer this into a buttered casserole dish. Oh, and do yourselves a favor. As soon as you have everything tossed and coated in that butter, transfer it immediately into the baking dish. Because what'll happen if you stop and wash your hands and move the tripod and change camera angles? That butter's going to cool off and congeal and look all clumpy like this. Okay, you see that? Yours is not going to look like that. But don't feel bad for me, it's going to be fine. I'll just have to give mine a toss halfway through the roasting, which by the way is not a bad idea, whether your butter clumped up or not. And yes, I just spoiled the surprise of the next step. Since what we'll do once we have that transferred in and distributed evenly is place these into the center of a 375-degree oven for about an hour or so, or until very, very, very tender. And how we know is we're going to test with the tip of a knife, and it should slide in with virtually no effort. So those were perfect. And yes, if you're doing this for a big holiday meal, all this can be prepped ahead, the potato part and the crumb part, and then you can just put it all together when the timing's right. And for that, we will go back and break up our crispy, cheesy crumbs. And as we place these on, I think we want to give them a nice pressing down, so those jagged shards of cheesy, crispy crumbs sort of adhere to those sweet potatoes underneath. And by the way, in hindsight, I wish I'd crumbled these up a little smaller, and you'll see why at the end when I'm enjoying some of these. But anyway, we'll go ahead and transfer over our crispy topping. And like I said, we'll give that a nice firm pressing. And then before this gets finished in the oven, I decided to grate down a little more cheese, which I thought would maybe sort of glue the crumbs together a little bit, which really didn't work. But on the other hand, more cheese. And that's it. This is now ready to finish off in the center of a 375-degree oven for another 15 or 20 minutes, or until everything's beautifully browned, and hopefully looking like this. And that's it. This is now ready to serve. But before I do, I like to take a barely damp paper towel and very lightly and carefully wipe those smudges off, just to make it look a little nicer. Although don't press too hard, or you will get burned. In fact, now I'm questioning whether I should have showed you that. But anyway, it does look nicer with a clean edge. And speaking of looking nicer, I went ahead and finished up with some freshly sliced chives. And that's it. My lemon pepper sweet potato crisp was ready to enjoy, which we could do right away hot. But here is some great news, especially if you're doing this for Thanksgiving or another special occasion dinner. I think this might actually be better warm or at room temp, since I find all the flavors come out even more pronounced. But also, when you do a cheesy, bready, crisp topping like this, it is actually, believe it or not, crispier once it cools. And if you've ever made Parmesan crisps, you know exactly what I'm talking about. So I did let mine sit and rest for a while before I served some up. And then after taking a few contractually obligated pictures, I grabbed a fork and dug in. And that, my friends, both texturally and flavor-wise, is just a magnificent bite of food. The only slight issue is that next time I'm going to break up that topping a little smaller and push it into the potatoes much deeper so that we get a little more adherence. Okay, that way we wouldn't have to do as much work getting everything on the fork. And yes, I use the term loosely. It wasn't exactly work, but a little bit smaller would have been a little more user-friendly. And then as far as the taste goes, I have absolutely no complaints. This was perfection. Okay, we have those soft, starchy sweet potatoes with the tanginess of the lemon and that little bit of heat and sharpness from the pepper. And when you add the extreme savoriness of that crust with that little touch of bitterness you get when you cook cheese crispy, it was just an absolutely tremendous combination of tastes. And of course, if you want to use different cheeses like Pecorino or maybe a Gruyere instead of cheddar, go ahead. I mean, you guys are for all the Chuck D's of which cheese. And this technique should work out just about the same no matter what you go with. But anyway, that's it. What I'm calling lemon pepper sweet potato crisp. I absolutely loved everything about this. And whether you're going to make it for a special occasion holiday dinner or just for some random weeknight supper, I really do hope you give this a try soon. So please follow the links below for the ingredient amounts, a printable written recipe, and much more info as usual. And as always, enjoy.
Okay.
Kind of like how a cube is a 3D square, a tesseract is a 4D cube, meaning every one of its faces itself is a cube. When you rotate it, it looks very weird and breaks my brain, and looking at it from this angle especially blew me away. You can rotate it out and see that it's the complicated tesseract rotation going on, but everything just blends together perfectly from here. I still barely know what I'm looking at. Happy Tesseract Week, everybody.
Putang ina! Si Optimum Pride! Puking inang yan, Optimum Pride! Babe, si Optimum Pride, oh!